Assume for the moment that you have $1,000 in your savings account. This is your starting amount. And every single week past this first day, you put $250 into the account. So let's think about a way to represent this data. So for instance, when we start, we have $1,000. And this, then, we can assume the next week, if we put $250 into there, don't take anything out, we'll have $1,250. And the next week, we'll have $1,500. The next, we'll have $1,750. And the last, we'll have $2,000. Obviously not the last, but we'll just stop there for now. We can represent this by saying, well, if we start with 1,000, we can kind of think of that as our 0th week. It's the 0 point. Then after 1 week, we have $1,250. After 2 weeks, we have $1,500. 3 weeks is $1,750, and 4 weeks is $2,000. We can represent this with a table. That's one way we can show this data. This is the number of weeks, and this is how much money we have. You can see that each increase is plus 250, plus 250, plus 250, and of course plus 250. And we can also write a model for this. If we have a starting point and we have a simple linear increase, meaning every single increase from the starting point to the next is always the same, in this case 250, then we can model this by saying we have $1,000 plus 250. I'm going to use the variable W to designate weeks. So in that case, we're saying that weeks is the W variable. You can of course test this. We get 1,000 plus 250 times W gives you 1,000. 1,000 plus 250 times 1 gives you 1,250, and so on and so forth. Now, we can also model this a little bit differently, and it might seem a little unusual at first, but just bear with me. Let's say we had a number line, and let's say we had 0, 1, 2, 3, and 4. Of course, the number line extends both directions, and our table could as well extend both directions. We just don't write any more than that. Now, let's designate the 0th number to be 1,000, the 1 to be 1,250, 2 to have 1,500, 3, 1,750, and 4, 2,000. Another way of writing this would be, instead of just writing the number above, is to put a dot, let's say 1,000 units away from the number line. So for instance, let's just consider for a moment that we say every 1,000 units we mark it as like an inch or something like that. It may not be an inch on your screen, but I'm just going to use an inch on my screen. So 1,000 units from the 0 is going to be about right there. And this is going to be 1,000. So we'll say this is 1,000. Then that means at 1, to get to 1,250, we're going to have an inch and a quarter, because a quarter of an inch is going to be the same as 250. So doing that gives us approximately right there. And that represents 1,250. Then that means after 2 weeks, it's going to be an inch and a half. 3 is going to be an inch and 3/4. And 4 will be 2 inches. Now, what's interesting here is that we can see that these 5 dots here fall along the same line, and they do. It is a linear relationship. We can draw a line through them, and we can actually put arrows on the end because we can just continue this trend. Now, if we wanted to make this a little more analytic, what we can do is we can introduce a second number line, and that we're going to create straight from the 0. And we can now label everything saying this is 1,000, right? And then we can go up to 2,000 here. I mean, we could label each one, give the smaller marks, little marks there, little tick lines, be 250 and so on. The same thing is true down here and above it as well, and then so on and so forth. And of course, we could actually create these long lines like this and create grid lines and everything like that. And what you end up getting is what's called the Cartesian coordinate system, named after Rene Descartes. He was attributed to it, but there's a lot of mathematicians were working on this at the same time. And the base idea is that you have two number lines that are overlaying each other at a right angle, and this allows you to graph in 2 dimensions. Now, there's a lot of interesting ideas about this, but probably one of the most significant is the idea that we took this, zoom out here, we took this linear relationship here, which had a table of values that we could do, and we created from it a geometric figure, one that is not algebraic, right? There's no algebra here. I'm not writing down equations or anything, but I'm showing the exact same relationship. This is 1,000 plus 250 W. There's a lot of nice visuals that math has if you can write it in the right way. And that's what this Cartesian coordinate system does. Now, a big part of this, of like college algebra, is talking about functions and graphs and analyzing them. And it all kind of boils down to understanding how do we look at the Cartesian coordinate system. It's quite a clever design, just two number lines attached at a right angle. And we always typically say the x-axis here is the independent axis, independent, meaning that it's the one that kind of dictates the values. In our model here, we had x, or in this case w, be the number of weeks. The number of weeks is when you kind of earn the money that you put into the account. And this, of course, is the dependent axis. This is typically the y-axis. I'll say x here, y here. And this depends upon the independent variables. Now, you typically use x for the independent, y for the dependent. That's just a convention for teaching this. It doesn't have to be the case. You can use, like we did here, w, and I could use m for money, w for weeks, and m for money. Here's just a basic number line. We can do 1, 2, 3, or basic graph, I should say. -1, -2, -3, 1, 2, 3. Typically, as we go up, we go positive. As we go right, because we like read left to right, we're going to the positive direction. So up and right are positives, down and left are negatives. And you can see there are 4 distinct, what are called quadrants, that are cut out by these 2 axes. And we always go quadrant 1 in the top right. That's probably the most useful axis or quadrant, because that designates real world application type things. We graph it in that quadrant. And then we go counterclockwise. So 1, 2, 3, and 4. They're always designated with Roman numerals. But you always go counterclockwise. This is a common theme in mathematics. Counterclockwise is the direction you want to go, so we go counterclockwise. But yeah, we have these 4 quadrants, and each one has different properties. For instance, if I were to ask, which quadrant has x times y greater than 0? X being the independent axis, the horizontal one, and y being the vertical or dependent axis. Which one of these quadrants has x times y greater than 0? Now we can't assume we're on an axis, because when you're on an axis, x or y, one of them, is equal to 0. For instance, if I chose this point right here, this point has y equal to 0. Right in the center dot, if you have any points lined up to the center dot here, one of the coordinates are going to equal 0. And so x times y is going to be 0, and that's not greater than 0. So we can't assume we're on one of the axes. We have to choose a point somewhere in there. So like, for instance, this point here, or this point here. Let me do them different colors. So blue is in the first quadrant, green is in the second quadrant. Let's do orange is going to be in the third quadrant, and purple is going to be in the fourth quadrant. Okay, just trying to clean this up a little bit. So you can test any points in these quadrants, because then it'll have the same property that the entire quadrant has when we're looking at these kind of problems. So for the first problem, right, x, which is at 2, you always go x first. It's going to be at 2. We're going to go up to 2. This point is called 2, 2. If we test that into our problem, x is 2, which is always the first, and y is the second. So x times y is 2 times 2, which equals 4, which is greater than 0. For the green, you always go x first, -2, then y. So we have -2, 1. Testing that, again, x and y is the coordinates. Coordinate is just the location of the point, and a coordinate always comes in pairs for a two-dimensional graph, or the Cartesian coordinate system is always two dimensionals. And a coordinate pair is written like this, 2, 2, or -2, 1. That's the address of the point. So we have x times y, which is -2, which is less than 0. Orange, x first, then we go down to y. We have -1, -3, not -2, -3. X times y equals 3, which is greater than 0. And finally, purple goes to 3, down to 3, so 3, -3. X times y, we get -9, which is less than 0. So which quadrants satisfy x times y greater than 0? Quadrant 1 and quadrant 3. Okay, now we've talked a little bit about the graph. Let's talk about plotting points on the graph. As I said before, you always start with the x coordinate. That's the ordered pair is always going to be x, y. And you always plot the x coordinate first, going left to right, and then going up to down to the whatever the y coordinate is. So for instance, -2, 4 in the blue, we're going to go over to -2, which is on the x-axis, is right here, and go up to 4. 1, 2, 3, 4. So right here is -2, 4. Okay, the green is 4, -2. We're going to go right to 4, and then go down to -2. You can, of course, just create a dotted line from the y-axis to figure out where you need to put the point. That goes right there. So 4, 2. Okay, -3, 0. -3 is going to be right on this mark there. And at 0, well, that means we don't go up or down at all. That means that is -3, 0. It's on the axis. The same thing is true for 0, -3. 0 means we do not go left or right at all, so we stay at the 0 mark, the origin, which is the middle point where the two axes cross. It's called the origin. And we go left to right, 0, and we go down to 3. So we go down right to here, and that's 0, -3. Finally, the purple shows that this isn't just integer numbers. This isn't just like whole integer numbers that we can use. We can also plot any kind of real number on the coordinate system. That's because they're two real number lines that are perpendicular to each other, which means they're all there. So 5/3, 9/2. 5/3, if you don't know, it's around, it's like 1 and 2/3, and 2/3 is about 0.66, I guess, but that's just 2/3 of the way up. So 1 and 2/3. Here's 1, and 2/3 is there's 1/3. That's about 2/3 right there. I'm going to go from this line up and down. 9/2 is going to be 4.5, right? And a half is just going to be 0.5. So I'm going to go up. It's positive to this right here is 4. There's 0.5. Go over. And right there is a pretty good estimate for 5/3 and 9/2. So using this idea of plotting points, we can actually plot graphs. To do this, we just create what's called a table of values. 5 to 7 values is typically the best idea. You can get away with 3 as long as it's a line, but a lot of times functions functions or graphs in general have different kind of behavior to where you need to have a lot more points to really see that behavior. That's why doing 5 to 7 is going to probably be your best bet. All right, here we've got a fresh coordinate system. Let's look at the graph of y equals 3 minus x squared. So I'm going to create a table of values. If you don't know where to start, probably a good place to start is right around 0. I'm going to start with 0. I'm going to go 2 back and 2 forward. Now all I have to do to figure out what y is, let me move this over some. All we have to do to figure out what y is we plug an x into the function. So y equals 3 minus x squared. X is -2 squared, or x is just -2. And so we get equal to -2 squared is 4. 3 minus 4 is -1. Plug in -1. And this gives us -1 squared is 1, and 3 minus 1 is 2. We get a slightly smaller marker here. Y equals 3 minus 0 squared. 0 squared is 0. 3 minus 0 is 0, so we get 3. Y equals 3 minus 1 squared. 1 squared is 1. 3 minus 1 is 2. And finally, y equals 3 minus 2 squared. 2 squared is 4. 3 minus 4 is -1. Okay, let's find these marks. We have, just to kind of make sure we're on the same page, if x, this is y here, if x is -2, y is -1. If x is -1, y is 2. 0 goes to 3, 1 goes to 2, and 2 goes to -1. Those are our 5 ordered coordinate pairs. Now let's graph them. -2, -1 is going to be -1, -2, and then -1 on the y. We get this point right here. Let's say -1, -1. Then -1, 2, we're going to go over to -1, then up to 2. So that puts us right here. This is 1, that's 2. 0, 3 means we stay on the y-axis and go up to 3. That puts us right there. 1, 2 means you go right 1 unit up to 2. And then 2, -1. Go over to 2, right to 2, and then down to -1. 2. And we put a smooth curve between these. So we go up, and we hit a peak, and we go back down. And this is what's called a parabola. It comes from a quadratic equation, which is what this is here. That's the shape that we get when we use a table of values to find this function. We also can have interesting graphs. So for instance, absolute value of x. The absolute value of x is also defined as x when x is greater than or equal to 0, or negative x when x is less than 0. This is called a piecewise definition of it. It has two parts. The top part is for positive x, positive or equal to 0x, and the bottom part is for negative x. It changes its behavior depending on where you're talking about on the graph. So let me draw the graph here. We just have straighter there. Not much straighter, but that's fine. Okay, let's create a table of values here. So I'm going to do the same kind of idea. I'm going to start with 0 and go -1, -2, 1, and 2. Now for the absolute value of x, if we plug in -2, we have to use the bottom definition, because when x equals -2, that satisfies this x less than 0. -2 is less than 0, which means we use -x. So this is going to be our y. Y equals absolute value of x, which for this definition we're going to say is -x, which is -2, which gives us the -2 is 2. We use -1. Again, we have this bottom case, x is less than 0, so we have the same kind of idea. Negative of -1, which is 1. Now when x equals 0, we have this top case. That's when x is greater than or equal to 0. So we have y equal to the absolute value of x, which equals just x, which is just 0. Of course, gives us 0. The same thing is true for 1. We have just x there. We get 1. And finally, 2 is the same thing. Gives us 2. And what you notice here is that all of these numbers are positive. And that's what the absolute value does. A lot of times it just makes the thing positive. So -2 goes to 2. -1 goes to 1. 0 goes to 0. 1 to 1 and 2 to 2. Plotting these points, I'll just create some ticks on there to keep us in line. -2, 2. We go left to -2, up to 2. Left to -1, up to 1. 0 goes to 0. Right to 1, up to 1. And right to 2, up to 2. And you would draw this as a smooth curve, but this one, if you draw more lines, which you'll see, or you put more dots into here, like -1.5, -0.5, 0.5, and 1.5. What you're going to see, you're going to end up getting this sharp line. You can keep putting dots, and you'll see that you have all of these dots along this line, all of these dots along this line. This one doesn't get a smooth curve. It actually gets this sharp point. Like that. And that's because of this piecewise definition. Not all of them follow this behavior. That's why you have to kind of graph it out. Also use graphing software. If you don't know a good one, you can always use desmos.com. M in there. Let me make sure I write it correctly. Desmos.com. You can always plug these things into graphing software to visualize what you're looking at. But in this case, we have a sharp point, and this is a interesting part of the graph. And that's typically why we graph these things, is to look for interesting behavior. And a point like this is very interesting. Another type of interesting behavior would be, say I have this graph here. Some more interesting points would be these points right here. And this point here. We draw it in a different color to distinguish. The red points are where the graph crosses the axis, namely the y-axis. And if it crosses the y-axis, these are called the y-intercepts. The blue point, of course, is where the graph crosses the x-axis, and these are called x-intercepts. Intercept meaning where it crosses. And these are very important for the graphs. We'll find out why a little bit later, but that's more features that we're looking for when we graph functions or equations in general. And here's my last question. Does -1, -9, that coordinate point pair, satisfy the equation 5x plus 8y equal 9? Now, if you were to do a number of points and to graph this thing out, which you'll see that this right here gives you this line right here. And we can look to see if -1, -9 satisfies this equation. To do it geometrically, all we have to do is find -1, -9, that coordinate pair, which is -1's right here, go down to -9. That's that point right there. And this equation or this question is pretty much, is that point on the line? Which it is not. So geometrically, we would say no. We can solve this algebraically quite easily by just plugging in the x and the y values into our function and seeing if we get a true statement. 5 times -1 plus 8 times -9 equals 9. 5 times -1 is -5 plus, it's going to be actually -72. And that gives us -77 equals 9, which is false. A false statement is the same thing as saying this point is not on this line. That's the algebraic version of the solution, and the right-hand side is the geometric version of the solution.